Hey guys, welcome to organic video 4. We're going to run through our organic reactions. So we are going to our packet page 8. And it would be really helpful also if you had your reference tables out. And went to table R. Remember that big one we watched in our last video. It's going to help us out a little bit. We might want a little P and Q as well, so kind of get to your organic tables. So, okay, so this is packet page 8. And this is our organic reaction. So we're going to start with the organic reaction of substitution. But before, let's review. I have inorganic reactions, which I didn't tell you before that they were inorganic, but remember, organic things are going to have carbon in them. So inorganic just doesn't have to have carbon. So remember, I had my synthesis, I had my decomposition, I had my single replacement, and I had my double replacement. So those were the previous reactions. We also learned combustion, but combustion is actually an organic reaction, so we'll go back over that as well. So remember, synthesis is when I take two things and I combine them. Decomposition is when I take something and I break it down. Single replacement, one thing tries to replace another. Double replacement is where two things switch. So now I'm in my organic reactions and I start with substitution. Substitution, let's see, is only alkanes because they are saturated. Only alkanes because they are saturated. That's important. We got to think about the bonds that an alkane has. Alkanes have that ane ending. If I go to table Q, I would remind myself they have single bonds. So alkanes have single bonds. That's what makes them saturated. And when I go through a substitution reaction, I'm actually going to replace one atom with another atom. So it's a lot like the single replacements would look like. An example of that, so let's say I have C2H6. And I'm going to react that with Cl2. So basically I have ethane and I have chlorine, and I'm going to react them. Well, let's kind of take a look at what C2H6 would look like. You'd have two C's. Here's my 6 H's. So if I look, it doesn't have any room for the Cl's to come up. It has no room at all. So remember that these lines to nowhere, they're really H's that would be on all of those. So for my Cl to jump on, it actually needs to take one of the H's off. So what happens is it does do that. And over here on the other side, I would have C2H5 and a Cl that would jump on. What would that look like? Two C's, 1, 2, 3, 4, 5, but maybe a Cl jumps on over there. And then I still have to think, okay, well, I'm missing something. I'm missing another Cl, and I'm missing an H. So I would also get HCl. So if I take a look at that reaction, I had an alkane. I tried to put something on. It didn't fit. So what happened was my Cl's that would be over here, they basically took off that H, and that H went on the other side with one of the Cl's, and the Cl jumped on. So substitution, I want you to think, biggest thing, think alkanes. So substitution we'll kind of put on the side or takeaways. So alkanes, remember I have to have those single bonds. I'm always going to get two products when I do these. Always going to have two products. That would be something to look for. Next one I have addition. Addition is when I actually add one or more atoms, but I got to do it at a double bond. Remember, those are alkenes. Or I can do it at a triple bond. Remember, that was my alkynes. So basically, addition, I need things that are unsaturated. Because when we think about unsaturated before, in a solution, we would think that means it's not full. Well, it's sort of the same thing here. If I have a double bond, I'm full. I have enough electrons. But if I want to add somebody on, it could share those electrons. So let me show you what that looks like. So let's say I have C2H4. Let's draw that. C2, so there would be two C's. And there would just be four H's. So let's see, if I just had, I'll put two over here, two over here. I would then realize that, hey, I need to have a double bond. Because remember, C has to have four bonds always around it. So there's my ethene. And I'm going to try to add Cl2. So if I do that, I can make that happen. So what I would get over here, I would have C2H4 Cl2. So I'm going to let them jump right on. So if I were to draw that, instead of right here where I had this double bond, see those C's are sharing them. So carbon doesn't really care if it doesn't share them. That would be okay for it not to share. So there's two electrons there. Remember, Cl, if I look at its Lewis dot diagram, it needs one electron. So it sees that bond and says, well, I can take one. And then the other Cl says, well, I can take one too. So they are basically coming over, going right at that double bond. So when they do that, they just jump right out. So now I have a single bond for my C's. My Cl's have jumped on, but now I still have those H's that I had before, so I didn't lose those. So in an addition reaction, we're going to think that I'm always looking for, well, this time I want an alkene, or I want an alkyne, because I want them to be able to take something else on. I want them to be unsaturated. And you're going to think that I'm always going to get, in this case, one product. This is very similar to your synthesis reaction. Very, very similar to a synthesis. Think of it like an organic synthesis reaction. That's your addition. Next, they come to fermentation. Fermentation is when I have glucose and I break it down into ethanol and carbon dioxide. So basically, think ethanol ends in OL, it's alcohol. And then I have my carbon dioxide, which is CO2. So I'm going to take glucose, which is really just a sugar, and I'm going to break it down, and I'm going to make alcohol. So fermentation always makes alcohol, in addition to carbon dioxide. So to make alcohol, what you have to do is you take your yeast. Well, what does the yeast do? So the yeast actually helps us along. It's an enzyme. So it secretes what's called zymase. So it secretes zymase, which is an enzyme. Okay, remember, those are like our catalysts that we had before. They help things fit together. And what that does is it's going to break down our carbon chain. It's going to break down our carbon chain. an example. Let me show you one. So I'm going to take that glucose, my C6H12O6, and here's what I'm going to make. I'm going to make ethanol. So think, if I went to my table R, which I could show you, remember that, where's my alcohol? Here's my alcohol. Right there. So my alcohol, I have an OH group. They give me an example of one propanol. I want to do ethanol, so just take one of the C's with H's out. I can do that. So I get C2H5OH, C2H5OH, there's my alcohol, my OH group, and so they also make CO2. I would then want to go and balance this equation. So to balance this equation, I have 6 H's here. To balance my H's now, I have 12 and 12. I got to balance my O's. So let's see, I have 4 here, 2 there. Yep, because I have 2 over there. So now everything would be balanced if I do that. So fermentation makes alcohol. Think this is how you make moonshine. Don't go making moonshine, but this is how you would do it. Fermentation gets your alcohol. So you're always going to look for an OH. Alcohols are going to have OH, but remember it's going to be with carbons, because if I just have an OH, it's a base. So fermentation makes alcohol. Next one, I have my esterification. So esterification has the word ester in it. So it actually makes an ester. So I want to think, well, what's an ester? I'm going to again go back to my table R. And I could see actually toward the bottom of what I have here. I can move it up, I think. Yep. Here is my ester group. I've got a C with a double bonded O and an O. If I look, I'll have that C with a double bonded O and an O, followed by 2 groups on either side. Remember, I end those in 08 when I do it. I name both sides of the chain. So now I know, remind myself of what an ester is. So we're going to say, okay, we know what that is. It's a C with a double bonded O, and it's got another O, followed by some chains on the side here. So there's my ester. There's my special functional group. So esterification is when you take an acid and an alcohol, and you're going to make an ester and water. So I have an example here. Let's decide first who's my acid and who's my alcohol here. So in this example, I see this C double bonded O, OH. That's my Q. So here's my acid. Plus, I have this OH here with C's. So this is my alcohol. So I have my acid and my alcohol, and I'm going to think, okay, I know I need to make an ester, and I need to make water. So I can do that. Think an ester at a C with a double bonded O and an O. Water, I know is H2O. So if I look here at my acid and my alcohol, I can form that water right here. See how I have an OH and an H? If I rip the ends off of those, I take the H off of my acid, I take the OH off of my alcohol, I've actually just formed that water, that H2O. So I've done that. So what's left? That's what makes my ester. So I'm going to take everything that was left. So I have this whole part. So I have a C with 3 H's on it. I have it bonded to a C with a double bonded O and another O. That's what I have left of my acid. Now in my alcohol, well, I took off the OH, so I have this stuff that's left. So I bond that with my O. So I have another C with 2 H's on it. I have another C with 3 H's on it. I just made my ester. I've got that group, and all I did was combine them. If we want to practice naming that, I would say, okay, I'm going to name the group on the side first. So I have two C's that are connected to this O right here. So two C's, so that would be an ethyl, that's F. So ethyl, two C's there, F, and OH. Ethyl, F, and OH. Water. So esterification will make an ester. Okay, we're going to the very next page. Very next thing, couple left. So a peptide linkage is special. I don't go too much into this, but a peptide linkage is when I do two amino acids. You don't really need to know amino acids, but amino comes from amine. And if I look at table R, amines have N. So these are going to have N in it. And you want to think acid that had that C with a double bonded O, and it had another OH on it. Sorry, that doesn't look so good at the top, but acid, I'm going to rewrite that. I hate that. So, let's see. Acid, C with a double bonded O, and an OH. So I'm going to have those groups in this. So if I look at the example right here, this is my amino acid. Because I see that piece right there, and I see this N right there. Okay, I don't want them to distract you, so I'm going to move them, but, well, apparently I'm not going to move that one. So, oh, my erase is off. Perfect. So here's my amino acid. Now I have to make over here this big little thing. Let's see if I can figure out what popped off, because it's kind of like my esterification. So let's kind of see. We'll have a C with two H's, an N with two H's, a C with two H's, an N with two H's. So actually, this part's the same. I have a C with a double bonded O, a C with a double bonded O, but then I go straight to an N. That doesn't happen here, so that must mean this OH pops off. So this is gone. Okay, this is gone. Let's see what's going on over here. I run into an N that only has one H on it. This N has two H's, so that means one of the H's popped off. Then if I keep looking, it goes to a C with two H's, a C with a double bonded O, and an OH. That's exactly what I have on my reactant side. So I popped off an H and an OH, also known as H2O. So if you ever see a peptide linkage, that's all I really need you to know. It's an amino acid, it's special. You don't really need to know that. But an amino acid has an amine group, and it has an acid group. And yeah, that's about it. So now, saponification. Saponification. Well, saponification is also known as hydrolysis, but really we'll call it saponification. And this is soap making. So literally, soap. So when I make soap, here's what I'm going to do. I'm going to take an ester, which is fat. I'm going to take a base. And what I'm going to form, I'm going to form soap and glycerol. Glycerol is a fancy alcohol, basically. So let's see if I can figure this out. So from my reactants, I'm trying to figure out, well, who's my ester and who's my base? Well, over here, I see OHs. So this must be my base. And actually, I have three bases. 1, 2, 3. And over here, I have an ester, but this is actually huge. This is huge. Look, 3 C's are all connected. And then coming off of them, I have these different chains of esters. So I have an O with a C with a double bonded O, an O with a C with a double bonded O, O with a C with a double bonded O. And then that's attached to C17H35. That would be huge if I drew that out. I don't have to, though, because I noticed that that's an ester. So here's my ester, or my fat. I have my base. So let's think over here. Which one's my soap and which is my glycerol? Well, glycerol ends in OL, so it must be an alcohol. And if I look, this has OH groups on it. It's a trihydroxy alcohol. So here's my glycerol. And so this must be my soap. Soap is really special. It helps us because it has both polar and non-polar ends, so it helps get the dirt off of us. And that's your biggest thing. Think whenever you're thinking saponification, I want you to think soap. It makes soap. Will you have to draw this? No. Will you have to recognize it? Maybe. But again, you're soap. Almost done, I promise. So combustion, complete combustion. You've been doing this. I take a hydrocarbon. I have to have it in oxygen. I need oxygen for things to burn, because remember, combustion is when I burn things. So, and then I'm always going to make CO2 and water. Always, always, always. So let's say I take C3H8. I just picked that. Doesn't really matter. It does not have to be C3H8. But I'm going to react it with oxygen, O2. It's going to burn. And I'm going to make CO2 and water, H2O. You always want to remember CO2 and water. That's always going to be your product. So then I got to go back through and balance stuff. So I'd grab my C. So I have 3 C's here. I have 1 here, so I'm going to put a 3. I have 8 H's on my reactant side. I only have 2 over here, so I'm going to do a 4. And then I'm just going to double check my O's. So I would have 6 O's in my 3 CO2. I would have 4 O's in my 4 H2O. So 6 and 4 is 10. I need a 5 in front of that O2. So combustion, I think you're pretty familiar with. Just remember that I always am going to make that CO2 and water, and I need oxygen for it to burn. Very last one, which I would say the Regents actually likes probably the most, because it's the most applicable to our real life, would be our polymerization. So polymerization is where I make really long chains. Really long chains. So things like plastics. I'll put them over here. So examples. Plastics is definitely one. Proteins. So if you, maybe I have some runners that are listening, or some athletes, and when you think that you want protein, right, for your muscles, and the reason why I eat proteins when I want energy is because it's made of really long chains. And so it takes a long, long time for it to break down. That means my body is going to have energy for longer. So when I look at polymerization, sometimes I'll see these words. So I might take a monomer and a monomer. Those are like small chains. And then I make my polymer, which is my really long chain. So if you see that word polymer, that's what you want to think. So monomers are just your small chains. Polymer is your long chain. So there's actually 2 kinds of polymerization. I can have addition polymerization. That's where I'm going to add to something. So let's say I have C2H2, but I have a bunch of those little chains. So let's say I have, that's my monomer, and I've got n numbers of them, so n times C2H2. Well, then really I'm just going to link them all together in a long little polymer. So I'd have C2H2 to the n, because now it would be attached. So it would be a super long chain. If you're doing condensation polymerization, think condensation, I need water. When I think condensation, I want to think water. So if I'm doing condensation polymerization, I'm going to have water and a polymer that's formed. Basically, I want you to really think that if I'm doing polymerization, I want them to reference that it has a really long chain. Or I want them to say the word polymer. Or I want them to say the word monomer. If I'm doing one of those, that's your polymerization. All right, guys, so now we're done with our notes. The only thing I want you to complete now, I want you to go in your textbook, and I want you to do page 208 and 209, questions 49 to 70. You do not do question 63. I will be checking that on Monday. This officially wraps up our organic unit. Very important. If you have any questions, you must ask me on Monday. Thanks, guys. Have a great weekend.